So what I did was I took these 1,000 data points as my population, and I picked 13 data points per sample, calculated a mean, sample standard deviation of the mean, and then I took this, which was not 2 times the standard deviation, but the critical t-score, and came up with my confidence interval. And then I asked the question, does the confidence interval contain the actual mean of the population over here, which is approximately 50? And so for most of the time, if you get a 0, that means, yeah, it is between these two values. But every once in a while, it doesn't happen. And it turned out 96% of the time, based on my samples, 96% of my samples, in this case, correctly predicted the confidence interval that included the sample mean. Okay, so I was trying to understand hypothesis testing too. So this is my attempt at hypothesis testing. So it's kind of the same thing, but in this case I'm using the critical t-score method. So basically what you do is you take the difference between the sample mean and the mean that you're comparing against, which is the null hypothesis mean, and try to determine whether that difference is statistically significant. So again, you have a sample of 13 data points, randomly chosen from 1,000 population, and you get the sample mean, standard deviation of the sample, standard deviation of the sample mean, and you can calculate a t-score instead of calculating a confidence interval. And if this t-score is greater than the critical t-score, then you reject the null hypothesis, and you say that there is a statistically significant difference. If the t-score is less than the critical t-score, then you fail to reject the null hypothesis. So therefore, you say there's no difference. And the critical t-score is a function of the number of degrees of freedom and the confidence, or well, what do you call that thing? The level of significance, alpha. So I think for all of these, alpha is 0.05. So you can look along here if you look at all these t-scores. So this one's, the critical t-score I think is 1.729. For that, let's see, here's 1.782. Okay, for 12 degrees of freedom, 1.782. So this one is very slightly greater than 1.782. This one's less. This one's more. And so where you get 0, you're rejecting the null hypothesis, even though there really is a difference, because the hypothesis mean is 48.5. The actual population mean is 50. So we know there's a difference, but the whole statistical process is trying to help guide you. And depending upon how close you are, if I change 48.5 to some other number, which I'll do in a second, you'll see that the percent of these tests that would reject the null hypothesis. So in this case, 65% of the time, I would reject the null hypothesis, and 35% of the time, I was failed to reject the null hypothesis, even though I know there is a difference. I mean, so it just kind of tells you that, if you run an experiment with a finite number of data points, even if you fail to reject the null hypothesis, it doesn't mean there's not actually a difference there. It's just you're not so certain about it. And I guess the closer you are, the closer these values are to the critical t-score, the more likely you should probably rerun the experiment, because you're going to reject the null hypothesis, fail to reject when you shouldn't. So you can see as I increase the difference between the actual mean of the population and the null hypothesis, you'll see that this number grows. So now 83% of the tests, the 83% of the tests on my random samples would reject the null hypothesis, and therefore there would be, we'd say that's significantly different. And it makes sense. The further the number difference between the numbers, the means, that the greater the chance that there actually is a difference. But I thought it was kind of interesting, just because you think when you do these statistics tests, you're 95% certain that there isn't a change, but that's not really true. It's a little more complicated than that. I'm not sure if I've convinced myself exactly what I know what's going on. I mean, the things that affect it are the number of data points. So I could have a smaller difference between my sample mean and my null hypothesis mean if I had more data points, because that would reduce this value. And also it would, if I could reduce the standard deviation of the temps samples, and because some of that's controllable and some of it's not. So if you don't do a very good job of measuring your variables, or you're not controlling other things that might affect the mean, then you're going to get more of a standard deviation. So if you can design an experiment to only change one variable and minimize changes in other things that also affect the final answer, the better chance you have of actually rejecting the null hypothesis when there actually is a difference in the mean. Anyway, I thought it was kind of interesting. So that's the difference between when you read a textbook one time or you take a class and then you think about it a lot. So I'm thinking about it a lot more so, just because I kind of like to know what if somebody asks me a question, at least have some idea. I think I know more about statistics now than I do about calculus. Well, not really, that's not true. Okay, so let's go back to our sheet. So how far did we go backwards? We were filling them out completely. And I have one for Mark here because he didn't have one yesterday. So we were starting at the back. Oh, you didn't. Oh, that's right. You didn't have that one. Let me see, Lexi.
Just did like the very back page.
The very back page, and then we were getting to. Okay, so there. Okay, so what we're basically doing is we're going back and filling in dotting all the I's and crossing all the T's. And so we are actually the one that's shown on the screen. So we did the actual test here. We used the limit comparison test because I know 1 over n diverges, so I'm pretty sure 1 over n minus 1 diverges as well. And so I can't, I think actually we said you could still use the direct comparison test, but the limit comparison test seems to be easier to apply. So what we did was we chose b sub n to be just 1 over n, and we proved that 1 over n is always less than 1 over n minus 1, which makes sense because when you subtract 1 from the denominator, this makes a smaller denominator, which makes a bigger fraction. But you can cross multiply and actually show it's true for all n. So that was true, and then you had to take the limit. I think that was on the next page. Maybe we did that. No, actually, I think you got to finish this off. So yeah. So what we've got left to do on this one is to take the limit of a sub n over b sub n. Look at your sheet for the tests, because you're not going to remember. I can't. So we go down to the limit comparison test, and it says as long as a sub n and b sub n are greater than 0, which they are, then if we take the limit of a sub n over b sub n, and that equals some value L, and that L is greater than 0, then if b sub n converges, a sub n converges also. if the same thing applies, then and B sub n diverges, which we know this diverges because it's a p-series. So you want to write all of that out. You want to write do the limit part of the condition of divergence, and then you have to say that this diverges because of something, which is the p-series. And then at the end you write down something like, because this is true and the limit does equal some value of L according to the and because B sub n diverges because it's a p-series with p, use the spell out what the convergence criteria for the p-series is with p equal to 1. Therefore the series diverges. Okay, so look at what we've done before. Try your best. I'll give you a couple minutes head start, and then I'll write it out. So, a lot of learning is looking at what you've done before, and then doing your best job to see the commonality between what you've seen before and what you're doing now. And then once you get good at it, then you might be able to do it without looking, but most likely you're going to have to look, so don't feel bad if you have to look at the previous examples that we did yesterday. If you want to ask your neighbor too, that's fine. So I'll leave you a little guide thing here. First, you're going to do you're going to take the limit of a sub n over b sub n, okay, as n goes to infinity. This is b sub n. This is a sub n. Put those in there, and then you ask the question: does it equal to L? That means just does it equal a number? 0, 1, 65. Just as long as it doesn't equal infinity. So that's the first thing you're going to do. And then we've already shown this to be true. Then you have to show that show b sub n, actually the series b sub n from n equals 1 to, I guess, from 2 to infinity, either converges or diverges. We already told you what it was, but it's a p-series. Okay, so just kind of sketch out, look what the convergence of this b sub n series is. Then you'll make some conclusion about that. And then you've put it all together into a nice, reasonably good English statement that explains why or why not the original series diverges or converges. Okay, so you got that part done. So now you're going to look at that. Look for the convergence criterion for a p-series and see what that is. So we've got all the good stuff here. We've proved this is true. We've shown the limit equals 1, which is finite. We've identified the B sub n series as a p series with p equal to 1. Okay, so now we're going to put all this together. So let's see how we'd put this. Okay. We could say for the series summation from n equals 2 to infinity of 1 over n minus 1, we will use the limit comparison test. Since, okay, we'll call it the alternate series is B sub n is the summation of B sub n from n equals 2 to infinity equals 1 over n. Okay. And then you could say something like, we can use the limit comparison test because B sub n, actually, we don't need to use it for that one, do we? That's not part of the limit comparison test. We don't even need that part, so we'll just ignore that. Yeah. That's one good thing for writing it out. You realize what you're doing. Okay, so we can use the limit comparison test because this is true. Because the limit as n goes to infinity of a sub n over b sub n equals 1, which is equal to n, L, which is less than, or greater than 0. Right? So that's really the only criteria that's required for the limit comparison test. That was for the that was if we wanted to use the direct comparison test. So that's that. If I confused you there, I apologize. Okay. So once we can say why we can use the limit comparison test, we can then say since the alternative series is a p series with p equal to 1, hence the convergence criteria for the p series is that if it's less than or equal to 1, which it is, okay, since this is a p series with p less than or equal to 1, this series diverges. Okay. Therefore, according to the convergence criteria of the limit comparison test, the original series also diverges. Okay. So let's review what I just said, see if I need to rewrite it. That's why I did so poorly in English. I never reviewed anything. Okay, so for the series 1 over n minus 1, we will use the limit comparison test. The alternative series should be is, not in. I'm always doing that. I was terrible at writing people letters. I'd always mess them up. is, glad I became an engineer. Okay. The alternative series is the summation from n equals 2 to infinity of b sub n, which is equal to 1 over n. We can use the limit comparison test because the limit of the ratio of a sub n over b sub n as n goes to infinity equals 1, which is equal to a finite number, which is greater than 0. And then since the alternative series is a p-series with p equal to 1, which is less than or equal to 1, this series diverges according to the criteria of the p-series. And then finally, we can then use the limit comparison test along with the convergence of the alternative series to also say that the original series diverges. Okay, so that's how that works. Yeah, no. Okay, let's try another one. So the one previous to that was summation from n equals 1 to infinity of the natural log of n over n to the n power. And we said that was the ratio test. So go ahead and look at, not the ratio, the root test. So if you look at your sheet, you'll see that the convergence criteria says if the limit as n goes to infinity, the nth root of the absolute value of a sub n is less than 1, it converges. And if the nth root of a sub n is greater than 1, as n goes to infinity, it diverges. So we just need to evaluate that, which I don't know how far we got. So this one's not going to be anywhere near as verbose as far as the... so what we would do is we take the limit as n goes to infinity of the nth root of the absolute value of the natural log of n over n to the n power. And the nth root of something to the nth power is just going to be equal to the expression, which is the natural log of n over n. And that's going to be equal to 0. We said L'Hopital, you could use L'Hopital's rule if you wanted to. You can look at the ratio, just how the two functions, how the two series, the natural log of n and n would grow as n gets bigger. So now that we have taken the limit of that ratio and we see that it's less than 1, so 0 is less than 1. So look at the previous one we did, see if you can come up with something that might explain word-wise. So you have to say something about, state what the original series is. State what test you're going to use. State the results of the test, or the convergence criteria for the test, and then make some conclusion relative to the result. I mean, you can look at it without writing all the words. You can see that because the limit is less than 1, then it's going to converge. Okay, so the answer is it converges. Just try to write something out without me doing it. Give it your best shot. I do have your tests to hand back today. We're going to do that at the end of class. You guys did better than last year's class on this test. That was good. I'm proud of you. So how was William and Mary?
I loved William.
Did you?
Yeah, we had an awesome day yesterday. We went to a mock lecture, and the professor was just really excited, and it was about Shakespeare, and I don't always love Shakespeare, but she was just so excited about it. It made it interesting.
So when you say mock,
So it was just the students who were there.
okay, so she was pretending. I mean, she wasn't teaching a real class.
Right. Yeah,
Okay.
it was tailored to us.
Okay, so it could have all been fake. No,
Well,
just
yeah.
just kidding. I
It's
mean,
not Henry the Fourth,
okay,
so
yeah. I mean her enthusiasm. Hopefully she has that enthusiasm. But anyway, just kidding. Go ahead.
I
I
don't
know.
think
Give
it
me a
could.
hard
I
time.
guess it
It
could.
could have been, yeah. She's an
Yeah.
actor. She's not really a teacher. This is like the on TV. This is an actor who's doing the TV. Go ahead, keep going. Anyway, it was good.
Anyway, yeah, just in general, it was good.
Yeah.
It made me realize that college is going to be really hard. It forced me to think really critically. So I knew that, but it was kind of a different level of
Yeah.
realization.
Okay, let me try my effort here. We'll say we will use the root test. Okay, that's all. You'd say that. So that's the test we're going to use. We could then say since the limit as n goes to infinity of the nth root of the absolute value of a sub n to the, just a sub n is equal to 0, which is less than 1, the series satisfies the convergence criteria therefore the series converges. Okay, so that was a lot shorter. Okay, here we go again. Let's go back one more. Yeah, the next two are pretty easy. So they're both geometric series, if you remember. So go ahead and give your effort here. It'll be kind of like the last one that we just did. You'll say something like the series is a geometric series. Therefore, we will use the convergence criteria for the geometric series. Also, when you have a geometric series, you're usually asked to figure out what the actual value is. So in addition to making some comment about convergence or divergence, you'll also want to calculate the actual value of the series. So the best thing to do is to identify it as a geometric series, then say for this geometric series R is equal to blah, which is less than 1, hence this geometric series converges according to the convergence criteria for the geometric series test. For the geometric series test, also the sum is equal to a over 1 minus r. So plug the numbers in, see what you get. A in this case would be, well, I went too far back here. We should be, let's do the one that's before that. So remember what we did for this one is we made it 1/2 to the n power. So a is 4 and r is 1/2. And do the same thing for the previous one to that. Yeah, no, you don't really want to write it out, but you still got to write it out. Yeah. This is actually being more, normally I've not, it's kind of like doing proofs, but which I'm not a big thrill of. I like to use the stuff, but so this is the one exception where I'm going to ask you to actually write it out. So Evan, are you good at English too? No. Yeah. I sympathize. I empathize with you. Do you like English? No, I don't either. Yeah, that's why yeah, it's hard to do this. I know for you non-English people, even the English people, it's hard to do. Okay. And this doesn't have to be exactly as I'm doing it, as long as you have the main elements. That's what's important. Okay. So do the same thing on the previous one. Just substitute in the appropriate numbers. So instead of 1/2, it'll be whatever. Yeah, did I do? Oh, is A equal to 4? Oh, yeah, I don't know why I wrote 6 down. I'm thinking of another problem. Thank you. Oh, it's because I was thinking of the other problem. That has 6. And I'm not going to write. I'm just going to let you guys write down the one for that. So don't wait for me to start because I'm not going to do it. Just identify the R and A and see what you get. I don't know if you noticed this morning the the there's no more space. This is the countdown. The countdown. How many do we have left now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 days. On the 12th day of calculus. Okay, I'm going to let you finish. If you haven't finished the previous one, I'm going to let you finish that. So you guys can we'll end up turning these in on Thursday. So we're going to move along to the next previous one, which was the summation from n equals 2 to infinity of 1 over the square root of n squared minus 1. And again, we said we're going to use the limit comparison test, and b sub n is equal to 1 over n for the same reason it was last time. Because if you drop this term and then you simplify, you get that. So you can actually go back to the description we had for this assignment. Okay, so I'm going to leave that up to you as well. So look what we wrote down for this one and apply it to this one, because there's really nothing, when you take the limit of this to using that as a sub n and b sub n as that, you're going to end up with a limit of 1, and that's going to satisfy the requirements for the limit comparison test. So likewise, this one here is using the root test. So again, you've already done the root test, so use that one to guide you in finishing that one up. That's before Thursday. Okay, let's go back one more here. If you have any questions, you can ask me later. So, Margaret, has your dad said exactly what he's going to talk about tomorrow, or do you know him?
Well, I thought that you wanted to talk about his cameras and kind of the evolution of film and
Yeah,
focus.
yeah.
Okay.
I mean, I talked a little bit about cameras yesterday, so when he talked, it wasn't the first time they'd seen it. But he can do it completely over again because I'm sure he has more insight into the whole thing. So.
And I know that the science fair is tomorrow. So
Oh, that's right. Yeah.
we're going to that too.
Yeah, I guess we should be able to go to that. So maybe we'll go. That's till 10:30, right?
Right.
Yeah. So we might go till maybe 10 o'clock in lab and then go over to the science fair. So.
We need to dress up because I remember last year they took a big group picture.
Not as seniors. I don't think the seniors have to do it. Yeah. Okay. So this one we said was using the ratio test. Is that right? Is that what you have written down? I think so. This one. Yep. Ratio test, yeah. Okay, and we went through it fairly heavily, so we just need to write a few words about the ratio test. So let's so for the ratio test, you take the limit as n goes to infinity of a sub n plus 1 divided by a sub n. And you should already have this written down. I'm just writing it down so we can see it on the board. So you'd have the limit as n goes to infinity of n plus 1 times 3/4 to the n plus 1 over n times 3/4 to the n. And we did it in class, and you simplified, and it came out to be 3/4. Was that what it was? Was that the limit? Yeah. So the limit was 3/4. So if you look at the convergence criteria for the ratio test, it says if the limit as n goes to infinity of the ratio, absolute value of the ratio of a sub n plus 1 over a sub n and less than 1, then it converges. So we would write something out like this. We would say we can evaluate the series using the ratio test since the convergence test, so I'm just going to explicitly write out what the convergence test is, but I'm not going to put I'm just going to show it as a sub n plus 1 over a sub n equals 3/4, which is less than 1, since the convergence test shows the limit, the series converges That's it. Okay, so that was pretty short and sweet. The one previous to that, I think we said we used the limit comparison test. Is that what we did? Yeah. So again, we've used the limit comparison test previously. So you can look at what you'll do is you'll take b sub n would be 1 over n, a sub n would be 1 over n, square root of n, natural log of n. And if you simplify that down, the limit of the ratio of a sub n over b sub n, what you end up with is, I think, 0, right? Ultimately, because the 1 over n's cancel out, and you end up with 1 over the natural log of it, square root of natural log of n, which goes to infinity. So you get 1 over infinity, which is 0. So I think what you find in this one is the limit goes to 0, and therefore the limit comparison test would. So look at the limit comparison test from previous examples and use the verbiage there. This one is just a p series, so that's a piece of cake. So I'm sure we wrote that down. P series. So you would write out something like this is a p series with p equal to 1.04, which is greater than 1. And if you look at the convergence criteria for the p series, you'll see that it converges if p is greater than 1. So you'll just, somewhere in your description, you'll say identify p, show that it's greater than 1, hence it satisfies the convergence criteria for the p series test. The one previous to that is summation from n equals 1 to infinity. This is something good to work on in study session. You can talk to each other about it. Okay, so this again also can be used using the limit. You could use the limit comparison test or the direct comparison test. Doesn't matter. Limit's kind of easier. You don't have to think as hard because you don't have to determine whether a sub n is less than b sub n all the time. So let's just use the limit comparison. The comparison we were using was 1 over n squared. And you can imagine that when you take the ratio of the limit of this, the limit of the ratio of these two, it's going to be equal to 1. And because 1 is greater than 0 and finite, and we've done limit comparison tests previously, so look at those. The telescoping series, let's talk about that one. What you need to do. We'll work through that one. So you're not going to help me at all, are you? Oh, actually, we need to talk about the test. So Mark's going to go take the test now. So we'll, yes, go ahead and try to finish that up by Thursday. Here it is. I'm going to stop my recording.